I'm sure you've seen movies with robots, and you might have wondered to yourself, how is it that they're so smart when the robots in your house, that is, your appliances and your toys, are just not as smart? Well, the good news is that scientists are working really hard to make them smarter and smarter. And it turns out the best way to do that is to make them more human-like, that is, to give them human intelligence. How do we do that? Well, we use something called deep learning to try and model the human brain. Now, the bad news is that doctors don't even understand in this day and age how the human brain works, why it makes the decisions that it does. And so this becomes an extremely challenging problem for us. And their inputs are not as helpful because we still don't understand how most of the things in the mind works.
Our brains are very great at processing information and recognizing patterns. Whether it's trying to predict the next word of a sentence when someone is speaking, or whether it's trying to detect an object from afar, our brains simply just understand these patterns and recognize these objects. At a very high level, the human brain is composed of neurons, stacked neurons, and these neurons allow us to recognize simpler patterns to more complex ones. And you could take, for example, a jigsaw puzzle. Let's say you don't have the box of the jigsaw puzzle, but then you start to build the puzzle and you recognize that there's some patterns that you recognize. There's a crowd of people, and then from the crowd of people, you recognize that they're at a park. And then that's exactly how the human brain works. You take simpler patterns to more complex ones, and you build context off that. And this is what motivates machine learning scientists to study the human brain and emulate the human brain using neural networks. And like I mentioned before, the human brain is composed of neurons, stacked neurons. And what makes deep learning deep is the fact that you have many of these stacked neurons.
One of the things that I personally find to be the most interesting about deep learning is that the mathematical framework behind it has been around for a really long time now. In fact, it's been around for more than 50 years. So how come they became so popular just recently? Well, the thing is, deep learning is actually a ridiculously compute greedy and data greedy technology. So it's only when we suddenly started having the proper computers to collect sufficiently enough data or to train these models that suddenly it became possible for data scientists to use them in practice. And what's differentiating those deep learning models compared to other machine learning models is mostly the fact that they don't attempt to make sense of an entire record, like an entire image, all at once. Instead, they have this interesting layered architecture that enables them to progressively convert raw information into something more sophisticated. So for example, when a deep learning model tried to make sense of image data, it would first attempt to combine several pixels together into an edge. And then in the next layer, it will try to combine several edges together into a small object. And then later on, combine several small objects into more sophisticated objects until it can finally make sense of the entire image and the entire scene. And so this has enabled us to do things we could never do before. For example, in the context of natural language processing, the task of trying to make sense of human language. Until the advent of deep learning, data scientists did not have a lot of options. In fact, most of them were using something called bag of words. And this approach was basically about trying to count the number of occurrences of specific terms or specific words in a sentence, a paragraph, or a document to try to make sense of its topic. And as you can imagine, this approach was making it extremely hard to differentiate a sentence such as this bagel is so bad and another sentence such as I want a bagel so bad, because the wording is so similar. But today with deep learning, we can differentiate these two sentences with no problem at all. In fact, a deep learning model would be able to tell you that these sentences are almost polar opposites of one another. So this is why data scientists are so excited about deep learning, and they're just barely starting to scratch the surface of what can be done with deep learning.
If you've taken a deep learning class, you've probably realized that image classification and natural language processing are two fields in which deep learning really has a tremendous impact. In the field of image classification, you've probably heard of the Alectio convolutional neural network. It's one of the canonical examples that represents one of the first times where convolutional, deep, dense layers as well as pooling layers were used in combination to predict what the label of an image is, making use of the natural properties of images we see in the real world. However, AlexNet is by no means a silver bullet to solve all of our image classification problems. It really was just a starting point. From there, we've seen recent progress in this field of image classification with the advent of new convolutional neural networks and related networks that are inspired by the fields of biophysics, computer graphics, and even human perception and cognition. This similar process has also occurred in the field of natural language processing. Take, for example, the RNN, or the recurrent neural network. This neural network is one of the first to understand that there is this time-invariant property of language, where words in certain contexts that appear at one time point will occur in a similar context later. They use this property to predict what language will be spoken in the future. This property has been taken and added on to by several other models, including the LSTM and the transformer networks, both which use context in different ways, mirroring the way in which we believe humans to perceive and process language. But by no means should we trivialize the amount of work that has been gone into making these models work and deployable in the real world. There's been a tremendous amount of interdisciplinary research that goes into really figuring out what parts of other sciences and studies should be used along with deep learning machinery to make the most effective model. There's also many hyperparameters such as the number of layers in the neural network, the deep learning network, and then the types of layers that are used, and even the connectivity of these layers that really has to be thought about in order to create a model that has high accuracy and is trained efficiently. So when we come and we want to train our own models, it's important to really think about the architecture and the different ways in which the individual components come together to create the larger model. Because if we don't do so, there might be biases that our model learns that we would be unaware of. So if we can't really think of these components individually and holistically as a larger part of our model, it might be best to just start with a simpler model and see where we can go from there.
As an ML practitioner, I'm sure you're familiar with the concept of deep learning. I'm sure you know that deep learning is something that scientists designed to mimic the cognitive ability of the human brain. From its inception in 1958 as a perceptron by Frank Rosenfeld, neural networks have seen significant amounts of progress over the years. Over the years, neural networks have taken giant strides in terms of architectures, loss functions, or even applicability of neural networks for different tasks. You would have seen neural networks being used to classifying single objects in a single image to detecting or localizing multiple objects in the same image. You would have also seen neural network architectures grow from deep, fully connected neural networks to single-stage detectors, two-stage detectors, encoder-decoder kinds of architectures, and so on. You would have also seen different types of loss functions being applied for different sets of tasks. That being said, as an ML practitioner, I'm sure you would have faced your own share of difficulties when applying some of the state-of-the-art models for your own datasets. I'm sure when you applied some of the state-of-the-art models to your own dataset, you would, even after doing some hyperparameter optimization, you would have still end up with suboptimal results on your dataset. The reason being that some of the state-of-the-art models have some inherent bias towards the dataset that they were built on. A lot of times you would have also faced difficulties in like getting suboptimal performances, even though you're training with a similar data set, but your data set might just be like out of distribution, and that's why you're ending up with like suboptimal results on your data set. Check out the link below to know more about some of the biases in neural networks for certain data sets. That being said, as an ML researcher myself, I'm particularly excited about the progress that is being made in this space as of now. But there are certainly a huge set of problems that need to be solved as soon as possible. Like some of the problems would include like explainability, for instance, is one sort of problem that we would want to address. We'd want to build like interpretable models so that like the models get better and we're able to diagnose the weaknesses of the models. Also, like extending research that you see on paper or applying research on your own data set is also a problem, because like a lot of us don't really know how to like better the research that is being mentioned in the paper as such. So significant time spent on this would help us build even more better models. I'm sure like as a machine learning researcher yourself, you would know how a gradient descent algorithm works, but as long as you don't know which loss function you should use for your own use case, you wouldn't know how your model works as such, or how your model is gonna work better with a better loss function as such. So I guess like a lot of research on understanding how or applying different loss functions, or when to apply different loss functions, would also help in like building better models yourself.